Now I am going to start module 4 of chapter 6. In this module, we shall discuss about solution of 3-dimensional wave equation. The module is divided into 2 sections. In first section, we shall find solution of wave equation using separation of variables method, and in the second section, we shall use Duhamel's principle to find solution of inhomogeneous wave equation. Now we are going to the slide presentation for deriving the solution using separation of variables method. I have already discussed the method of separation of variables to find solution of Laplace equation, heat equation, and also wave equation in 1 dimension and 2 dimension. Now I am going to apply this method to find solution in 3-dimensional Cartesian coordinate system. The wave equation in Cartesian coordinate system can be represented by the equation given by equation number 1. As usual, we write the solution u as product of 4 functions capital X, capital Y, capital Z and tau, where capital X, capital Y, Z and tau are functions of small x, small y, small z and t respectively. Now substituting this solution to equation 1, we get an equation which is written here 1 by capital X d2x dx square plus 1 by y d2y dy square plus 1 by z d2z dz square equals to 1 by c square tau d2 tau dt square. So, first of all, we are separating the function of t from the function of x, y and z. So, that is why we write the expression in t tau in the right hand side. Now, to get a periodic solution, we are assuming the separation constant as a negative number. So, in this case, the value of the separation constant is minus omega square by c square. Now, using this separating constant, we again separate the function of z from the function of x and y, and that is written in the second line 1 by x d2x dx square plus 1 by y d2y dy square equals to minus 1 by z d2z dz square minus omega square by c square. We are assuming here the separation constant as n square. In the last line, we are separating the function of x and function of y, which is written here 1 by capital X d2x dx square equals to minus 1 by y d2y dy square minus n square, and we are taking another separating constant as minus p square. Therefore, all the equations for capital X, capital Y, capital Z and tau can be expressed in the form which can be seen in this slide. The solution for capital X can be written easily as C1 cos px plus C2 sin px. Now, if we look at the equation for capital Y, its solution is also linear combination of sine function and cosine function. So, the solution for y can be written as capital Y is equals to C3 cos qy plus C4 sin Qy, and the solution for Z can be written as capital Z is equals to C5 cos Rz plus C6 sin Rz, and the solution for tau can be written as tau equals to C7 cos omega t plus C8 sin omega t. And it is clear from the solution that it is periodic with respect to time and its period is 2 pi by omega. So, the solution of the original equation or the 3-dimensional wave equation can be written as u is equal to capital X into capital Y into capital Z into tau, which is given here in equation number 2, where the constants P, Q, R, Z, R, omega are given by the equation Q square equals to n square minus P square, R square equals to omega square by C square minus n square, and P square plus Q square plus R square equals to omega square by C square. Now, we are trying to find the solution of wave equation in cylindrical coordinate system. The wave equation in cylindrical coordinate system can be expressed as it is given in equation number 3. Del 2u del t square equals to c square into del 2u del r square plus 1 by r del u del r plus 1 by r square del 2u del theta square plus del 2u del z square. Now, to apply the separation of variables method, we write the solution u as product of capital R, capital theta, capital Z and tau, and we substitute this solution to equation 3 and we obtain the relation 1 by capital R d2r dr square plus 1 by r dr dr plus 1 by r square theta d2 theta d theta square plus 1 by z d2z dz square equals to 1 by c square tau d2 tau dt square. So, first we are separating the time variable and we are assuming the separation constant as minus omega square by c square to obtain a periodic solution of the given equation. Now, using that separation constant, in the next line we are separating the function of z from function of r and theta. So, the we get the equation 1 by r d2r dr square plus 1 by r dr dr plus 1 by r square theta d2 theta d theta square equals to minus 1 by z d2z dz square minus omega square by c square equals to a separating constant minus n square. Again we are separating the function of r and function of theta in the last line. So, it becomes r square by capital R into d2r dr square plus 1 by r dr dr plus n square r square equals to minus 1 by theta d2 theta d theta square is equal to a separating constant m square. Therefore, the equations for r theta z tau can be written in the form which you can see in this slide. So, if you observe the tau equation, so it is very easy to find solution of this equation. So, its solution is linear combination of sine function and cosine function. So, this is periodic with period 2 pi by omega So, the solution for tau is tau equals to some constant C7 cos omega t plus C8 sin omega t. Now, if you look the Z equation, it is given by d2z t z square plus q square z equals to 0. So, its solution is C5 cos qz plus C6 sin qz. Now, if you look at the theta equation, its solution is again linear combination of sine function and cosine function. So, its solution is C3 cos m theta plus C4 sin m theta. Now, the equation for capital R can be seen, it is given by d2r dr square plus 1 by r dr plus n square minus m square by r square into capital R equals to 0. And this is famous Bessel equation of order m. So, its solution is linear combination of Bessel function of order m. So, its general solution is given by C1 Jm in R plus C2 Ym in R, where Jm Ym denote Bessel function of order m and of first kind and second kind respectively. Therefore, the solution of wave equation in cylindrical coordinate system is given by u equals to capital R into capital theta to capital Z into tau, which you can see in equation number 4. And in this solution, the constants C1, C2, C3, C4, C5, C6, C7, C8 are arbitrary, and the values of these constants can be obtained from the initial and boundary condition of the given problem. Now, I am going to discuss the solution of wave equation in spherical polar coordinate system. The wave equation in spherical polar coordinate system is given by equation number 5. As usual, we are assuming the solution u as product of 4 functions capital R, capital theta, phi and tau, where these are function of smaller, small theta, small phi and t respectively. So, substituting this solution to the original equation 5, we obtain the relation which you can see in the last line. So, first of all, we are separating function of time or t from the function of r, theta and phi. So, first we are assuming that the solution is time periodic. So, the separation constant is taken as a negative number. So, that separation constant for this problem is minus omega square by c square. So, using that separating constant, we then separate the function of phi from the function of r and theta. So, in the first line you can see that we are separating phi from the other two variables r and theta, and we are assuming the separation constant as m square. Now, using this separation constant, in the next line we are separating the function of r and function of theta, and the separation constant for this case is n into n plus 1. Now, all the equations means the equation for capital R, capital theta, capital phi and tau are given by these 4 equations. So, if you observe these equations, so let us first start with the tau equation. So, from tau equation you can see that the solution is periodic in time. So, its general solution is written by some constant C7 cos omega t plus C8 sin omega t, and if you look at the phi equation, its solution is also the linear combination of sine function and cosine function. So, capital phi is equals to C5 cos m phi plus C6 sin m phi. Now, if we look the theta equation, the theta equation is not familiar to us, but if we do some substitution, that means if we put cos theta equals to some variable mu, and if we write the equation in terms of mu, that means if we change the independent variable from theta to mu, we shall obtain Legendre equation. Rather, we can say that we will get an associated Legendre equation. So, its solution is the linear combination of associated Legendre function. If you give a transformation to the dependent variable in such a way that capital R equals to R to the power minus half into capital S, it can be shown that capital S will satisfy Bessel differential equation of order n plus half. So, the general solution for capital S can be written as C1 j n plus half mu r plus C2 y n plus half mu r, where j and y are Bessel function of first kind and second kind and of order n plus half. Therefore, the solution capital R can be written as capital R equals to R to the power minus half into S. Therefore, solution of wave equation in spherical polar coordinate system can be written in the form which you can see in this slide. In the last section, we have discussed about solution of homogeneous wave equation using separation of variables method. But it is also necessary to find solution of inhomogeneous wave equation, because this type of equation arises in electromagnetic theory and other branches of mathematical physics. Now, we shall use Duhamel's principle to find solution of inhomogeneous wave equation in terms of the homogeneous wave equation. Now, we are going to our slide presentation. In this section, I shall discuss Duhamel's principle for wave equation. Here, I shall show that how the solution of inhomogeneous wave equation is related to the general solution of homogeneous wave equation. Consider the Euclidean 3-dimensional space R3 and a point xyz belongs to R3. Suppose V is function of x, y, z, t and lambda. Lambda is some parameter which satisfies the partial differential equation del 2V del t square minus c square Laplace square V equals to 0. That means, V satisfies the homogeneous wave equation together with initial conditions V x, y, z 0 lambda equals to 0 and del V del t at x, y, z 0 lambda equals to f x, y, z lambda, where capital F is a continuous function of x, y, z defined in R3. Now, we define a function u which is function of x, y, z and t, and which is defined in this way: u equals to integration 0 to t v x, y, z t minus lambda lambda d lambda. Then we propose that u satisfies the equation del 2u del t square minus c square Laplace square u equals to f with initial conditions u equals to 0 and del u del t equals to 0 at the point x, y, z and 0. That means initially they will u and both del u del t are 0. Now to establish that, we differentiate u with respect to t. So, if you look at equation 6, if you take the differentiation of u with respect to t, so this is differentiation under the sign of integration. So, according to that rule, its value is equals to v at the point x, y, z, and we have to put the value of lambda as t. So, if we put value of lambda as t, the fourth argument becomes 0 and lambda is t. So, the first element is v x, y, z 0 t plus integration 0 to t del v del t x, y, z t minus lambda lambda d lambda. And we have that v, if you look at this equation, v at x, y, z 0 lambda is 0. So, if we use this condition, the first part becomes 0. So, del u del t becomes integration 0 to t del v del t x, y, z t minus lambda lambda d lambda. Again differentiate del u del t with respect to t again. So, left hand side is del 2u del t square, right hand side is again differentiation under the sign of integration. So, the first element is del v del t at the point lambda equals to t. So, this is del v del t at the point x, y, z 0 t plus integration 0 to t del 2 v del t square x, y, z t minus lambda lambda d lambda. And the value of del v del t is given here. Del v del t at t equals to 0 is given by f x, y, z lambda. Therefore, the value of del v del t at x, y, z 0 t is equals to capital F x, y, z t. So, if we substitute it here, it becomes capital F x, y, z t plus integration 0 to t. The value of del 2 v del t square is c square Laplace square v, because v satisfies the homogeneous wave equation. So, using that fact, we can substitute the value of del 2 v del t square as c square Laplace square v x, y, z t minus lambda lambda d lambda. Since this Laplace square is the operator, this is the differential operator with respect to x, y and z. So, we can take out this differential operator from the integral sign. So, it becomes c square Laplace square operating on 0 to t v x, y, z t minus lambda lambda d lambda. So, that is nothing but u. So, in the next line we can write it as f x, y, z t plus c square Laplace square u. Therefore, u satisfies the wave equation, inhomogeneous wave equation which is written in equation number 7. And you can prove that value of u at x, y, z 0 is 0 and del u del t at x, y, z 0 is also 0. Therefore, the solution of wave equation, not wave equation, this is so inhomogeneous wave equation, can be written in terms of the solution of the homogeneous wave equation, which is given by equation number 6. In this way, we can find the solution of inhomogeneous wave equation, that means u, in terms of the solution of the homogeneous equation, that means v, which is written in equation number 6. Thus, in module 4 of chapter 6, we have discussed about the solution of 3-dimensional wave equation. We used separation of variables method to find solution of homogeneous wave equation. We have discussed 3 separate cases. In Cartesian coordinate system, the solution is mixed Fourier function. In case of cylindrical coordinate system, we obtain mixed Bessel and Fourier function, whereas in case of spherical coordinate system, we obtain the solution as mixture of Bessel, Legendre and Fourier function. We have also derived the solution of inhomogeneous wave equation using Duhamel's principle. There we have shown how to write solution of inhomogeneous wave equation in terms of the general solution of homogeneous wave equation. Now we end this module.